Okay, so in this chapter we're going to rederive the multidimensional chain rule from the one-dimensional case and then introduce the notation we're gonna use for the rest of this series. So let's start things off with a very simple case. Let's say we have two functions f and g, where f goes from r1 to r2 and then g goes from r2 to r1 again. And then we define h as the composition of g with f, and h goes from r to r again. And then the question becomes, what is the dx of h? Okay, and in order to answer that question, I want to draw a little something first, so that we can get an intuitive understanding of the multidimensional chain rule. Let's assume we have the real number line here, and we have some point along that line that we call x. Then what f is doing is that it's mapping this point onto some other point in the two-dimensional plane. And then g comes in and moves this point again onto a point on the real number line again. Now the point in the middle we could call f1 of x and f2 of x, where f1 and f2 are the component functions of f. And the point below is what we would call g of f1 of x and f2 of x. Okay, and now if we ask what the derivative of h is, and remember h is the composition of f and g, then we're basically asking how a nudge in that direction affects this point here, affects g of f of x. And now let me state what we already know from one-dimensional calculus. We can compute how this point below moves when we move this point in the plane in the x direction, and we know how this point moves when we move it in the y direction. Now, why do we know this? Well, because if we fix this second component, for example, then what we get is a one-dimensional function. Let me state that again because that's important. If we fix one component of g, then g becomes the function from the real number line to the real number line. This means that if we fix the second component here, which is movement in this direction, then the movement we are left with is movement in the left and right direction. And this is how we compute the derivative of g with respect to the first component. It's by fixing the second component and only looking at the nudge in one direction. And we can do the same for the other component, of course. We can fix the first component, which is movement from left to right, and then only move the point up and down to see how the output changes. And now what we also know is the derivative of the component functions, because the component functions are also one-dimensional. The first component function describes the position of the point in the first direction and the second component function in the other direction, which means that we can differentiate the component functions with no problems. Okay, and now let's try to put this all together. So we nudge x in this direction and we call the nudge dx. Then maybe the first component function moves this point in this direction. So you could think of this as f1 of dx. And now the other component function might change upwards, but maybe not so much as the first component. Okay, and what we know is how g changes when we nudge it in the x direction, and we know how g changes when we nudge it in the y direction. Okay, but now notice that the nudges aren't of equal size. The nudge in the second component is much smaller than the nudge in the first component. And this is why when computing the derivative of a chain function, we multiply the outer derivative with the inner derivative. The outer derivative tells us how much the function changes with a unit nudge. Let's call it the unit nudge. But the inner derivative tells us how big the nudge actually is. Because in this case, maybe the nudge is smaller than the unit nudge, and maybe this one is larger than the unit nudge. So we have to rescale the unit nudge with the appropriate amount so that the final result is accurate. Okay, and the last thing that's left to do when going from one dimensions to the multi-dimensional case is that we have to add all of those different influences together. So maybe the blue nudge is nudging g in the positive x direction, whereas the smaller green nudge is nudging it backwards. Well, then the resulting nudge is just the sum of the two individual nudges. Okay, and at this point it's already time to clarify some things. So there is a difference between computing the differential of a function just in general for every point, or computing the differential on one specific point. And the difference between those two is that the first method gives us back a function, and the second method gives us back a concrete value. And here what we have computed is the differential of a single point. And so in order not to confuse the name of the point with the name of the variable with which we want to differentiate, I will name this point x0. So notice that x0 is just a fixed point on the real number line. And now what we can do is we can compute the differential of h and then evaluate this function at a specific point, which we will call x0. And so this line here, this is notation you probably haven't seen, but this means nothing else than evaluating this function at this point here. Okay, and as we have just clarified, this is nothing else than the partial derivative of g in the first component, which I call x, evaluated at the point f1 of x, times the derivative of f1 with respect to its only first component, and evaluated at the point x0. Okay, and the reason I'm writing partials, even though f1 is just a simple one-dimensional function, is because in the Jacobian matrix of a function, we also write partials because we split the function f up into its multiple component functions. Okay, and remember that this was just the influence of the first component. So when, for example, ignoring this entire axis and ignoring this, but we still need to add the influence of the other component. So we have plus the partial of g with respect to its second component, which I call y, and we evaluate this derivative at the point f2 of f of x, and we multiply this with the partial of f2 differentiated with respect to its only variable x, and again at the point x0. Okay, that seems like a lot. So I think it's time to do a little example in order to clarify the things we're doing right here. So let's say f of x was defined as the tuple x squared and, I don't know, sine of x. And now let's say that g of xy was defined as x times y. And let's choose a point x0 on the real number line, let's say 2. Then the differential of h with respect to its only component x evaluated on the point 2 is nothing else than, well, I'm just gonna copy this formula and now replace all of the variables we know. What is g again? Well, g was x times y, and we want to differentiate it with respect to the first component and then evaluate it on f1 of x0. But f1 of x0 is just the point 2 squared, which is 4, and sine of 2, which I will not compute now. Okay, and this we multiply with the partial derivative of f1 of x, which is x squared, and we evaluate this at the point 2. And now we add the influence of the other component, so it's the same here. We have the function x times y, but now we differentiate with respect to the second component y, but the point on which we evaluate is the same, it's 4. I noticed I made a mistake. We are using the entire f to evaluate the function, because differentiating with respect to g's first component already tells us that we need to fix the second component. But then of course we need to know where we want to fix the second component, which is why we need both components of x. The first component, which we will plug in later, and the second component, which tells us at which point we fix the second component. So then we have here the same point 4 and sine of 2. And we multiply this by the derivative of the second component of f with respect to its only component x, and evaluate it on the same point too. Okay, so what is that? Well, if we fix the second component y here, then the differential of this function with respect to x is just y. So the x just vanishes, we don't use it anymore. So we have sine of 2 here times, what is that? The derivative of x squared is of course just 2x, and we evaluate 2x at the point 2, so we get 2 times 2, which is 4. And now we add the rest, and here this is the same if we differentiate x times y by fixing the first component and differentiating with respect to y, we only get x, and we evaluate the function x where the y just vanishes at the point 4 sine of 2, which gives us just the x component, which is 4. So we get 4 times, oh, I didn't write out the derivative, but f2 is just sine of x. And so the derivative of sine of x is, of course, cosine of x. And x in our case is 2, so we get cosine of 2. And this here is just a real number. Now, if I wanted to compute the entire derivative on every point, I wouldn't have plugged in a point 2. I would just have left it as some abstract variable. Maybe I could call this variable z or something. And then every time I would have plugged in 2, now I would plug in z and see what results at the end, which would give me a function from r to r where I plug in z and I get some value that depends on z. But in the case of our neural networks, we are not interested in the entire derivative because we can't set the entire derivative to 0 and then solve for the input. Instead, we want to compute the derivative at a specific point and look at the gradient in order to do the gradient descent algorithm. And now it's time for some new notation again. Because when computing the gradients, we will in fact not differentiate between the name of the point we plug in and the variable with respect to which we want to differentiate the function. So I will write the sentence down and then look at what it does to our example. From now on, we don't distinguish between the point in which we want to evaluate the differential and the variable with respect to which we differentiate the function. So what this means for our example is that instead of writing dh over dx and evaluating this differential at the point 2, we would instead just write dh over d2. Now, I know this looks very weird, and when calculating the gradients, we will in fact not use a real number here, but we will use a variable. But it's important to know that this variable, although it has a name, is actually just a real number. And when I first started calculating the gradients, I got very confused sometimes because I always forgot that the variable with respect to which we differentiate also then immediately gets plugged into the differential. Okay, so what would this notation look like? Well, dh over d2 is the same as, well, g is nothing else than x times y, but there is no x and there is no y. Instead, we have to use 4, which is 2 squared, times sine of 2 in order to describe what the function g does, and we want to differentiate it with respect to the first variable, which is 4. And then we multiply this with 2 squared, which is the function, with respect to the variable 2, or the point 2, because it's the same. And now we add the differential of the same function, 4 times sine of 2. We differentiate with respect to sine of 2, which is the point of the second component, and we multiply that with sine of 2 differentiated with respect to the only variable 2. Okay, and now we can do the exact same calculation. The differential of this is just sine of 2, so we just copy that. And now 2 squared differentiated with 2 is just, well, the exponent moves here. We have 2 times 2, so we can write 4 immediately. And now differentiating this expression to the second component function gives us 4, and the differential of sine of 2 with respect to 2 is just cosine of 2. And as you can see, that's the exact same number we got out the first time. Okay, I hope that now you understand how the notation works exactly. But we haven't actually done the general case of multidimensional chain rule. We have just done a very simple example. But still, I think that this little example is enough to motivate where the definition of the multidimensional chain rule comes from. Because if we take a look at this expression again, which I will just copy to have a bit more space, then we can express this as a matrix multiplication of 2 matrices. The first one, I'll just do it like this. And the second matrix is the one that contains those 2 entries here. Okay. And now if we multiply these matrices together, we get the exact same expression we just had. And hopefully by now you notice that this is just exactly the Jacobian matrix of the 2 functions. So another way to write this, and this way is much shorter, is to just write the Jacobian of g evaluated at the point f of x naught times the Jacobian of f evaluated at the point x naught. And that's probably the most precise and most compact way to write things. Okay, but this is still not the final notation we're going to use for the rest of this series. Because if we want to differentiate functions that are longer and longer chains of other functions, then it's very annoying to keep track of all of the inner functions that you have to write down here into the Jacobian. So what we're going to do instead is we're going to write the Jacobian as follows. del g over del f times del f over del x. And now notice that I have omitted the x in the argument here, because as you may have remembered from the last video, the expressions can get really long and we don't want to write out all of the arguments every time. This would be madness. So instead we omit all of the arguments and just remember which argument came just right before that. And so the bottom line is this. This here is just a point on the real number line. This here then becomes a Jacobian that's already evaluated at this specific point. And because f of x is a specific point, this here is also a specific point, which means that this here is the Jacobian evaluated at a specific point, namely f of x. Now, there are other ways to write it down. And I have seen, for example, that some people write something like this. And this is totally valid. I mean, this gives the exact same result as what we had here. We multiply this times this, and then we add this times this. However, I don't like this notation, because if we have longer and longer chains, then we get more and more sums. Because imagine this instead of x were just another function, for example h. Then we would need another index in order to differentiate h with respect to x. And we would need another sum in order to sum all of these influences. But we can have chains that are much longer, and I don't want to keep track of more indices. So the less indices, the better in my opinion, which is why in our case, it would just look like this, which I find much easier to look at. Okay, and that's it for the notational part. Now you know how the multidimensional chain rule works, and you know how we are gonna write things down. The last thing I want to do in this video is to help you keep track of the dimensions of the Jacobians. So if we have an expression that looks like this, delta f over del x, then this in general is a matrix. Now remember, in our example, x was just a one-dimensional value, but when computing the chain rule, most of the times this will be a multidimensional vector, and this will also be a function with multiple components. And so what we get is a matrix, let's say n times n, where the first entry tells us the number of rows, and the second entry tells us the number of columns. Okay, I hope you knew that already, but honestly, I think there's another and maybe superior way to think of the dimensions of a matrix, which is what I want to share with you. So instead of thinking number of rows, think of it as how long is a column vector? And think of the number of columns as the other question, how long is a row vector? And the reason I like this way to think about it is that if I tell you M is a matrix of dimensions, I don't know, 10 times 2, then it would be great if you immediately knew whether the shape was like this or whether the shape was like this. And if you remember that the first number tells us how long a column vector is, you know that if the first number is very large, then the column vectors are very long. So in this case, we get a matrix that looks like this. Now, the last thing to know is that f in this case is a function that goes from Rm to Rn. Or in other words, the entries x1 through xm form the rows of the matrix, because here, how long is a row vector? So x1 is in the first entry of the row vector, etc. until xm is the last entry of the row, whereas the f component functions form the column. Okay, so if we layer these over one another like this maybe, then we get a matrix that would be the Jacobian of f. So maybe I can just color these values blue and these values red in order to be consistent with the colors I've just used above here. So the f's here form the column vectors of the matrix and the x here form the rows. Okay, so that's everything for this video. In the next one, we will finally be able to compute the derivative of the big L loss function with respect to some parameters. Not all of them, only the last layer, but computing these is already half of the work, because the other layers generalize pretty easily from that. So then, I hope you've enjoyed this video, and I see you in the next one. Bye!